So here we said we are going to discuss tree pruning, because we said chances are high that we are going to overfit, right? Chances are high we are going to overfit the data, leading to poor test results. Because now, if let's say each observation has its own region, that's the extreme case. Each observation has its own region. We've overfit completely. A test observation where we are not going to know where to put it. We are not going to know where to put it, right? So if the resulting tree is too complex, what we can do is we can plant a smaller tree with fewer splits, that is fewer regions. So we want fewer regions, J. So as long as this is going to be a small tree, we want it to be a small tree, right? So instead of each region now having only one or two observations, maybe we'll plant a small tree such that each region ends up with like 15 or 20 observations, and that will just be maybe with few splits, maybe something like this, instead of 20 splits. You know what I mean? 20 levels or whatever you want to call them, right? So this might lead to lower variance. Small tree will lead to lower variance. Why? Because the tree will not change that much depending. It's not that heavily dependent on training data. If each region had one observation each, it means changing one observation will change the whole tree. We will get so confused because it's heavily dependent on the training data. But if each region had 20 observations in it, changing one observation might not affect the tree that much. So it means a smaller tree with fewer regions will have lower variance. It will have lower variance and better interpretation at the cost of a little bias. Of course, if you have lower variance, you probably have a bit more bias, just because of the variance bias trade-off, the bias variance trade-off, right? So one possible alternative to the process described above that we did in the previous video is to build the tree only so long as the decrease in RSS due to its split exceeds some high threshold. So we say, because previously we said we can plant the tree and keep reducing the RSS, because that was the idea, right? Keep reducing the RSS, but we might say plant the tree reducing the RSS until you get to this RSS, until you get to a threshold RSS, and then we say stop. After that, we stop planting the tree. We stop splitting. When you say planting the tree, we stop splitting. We stop splitting, right? So this will result in smaller trees, but it's too short-sighted. Since it's too short-sighted because we said this tree does not care what happens what happens later. It's the way we plant the tree. It's greedy. It's just going to care about the split there, and it doesn't care that maybe later the variable that I'm going to use to split is going to result in much greater decrease in RSS. The tree does not know that. It's short-sighted. It deals with the node that it's dealing with right now. So a seemingly worthless split earlier on, that could be here, might be followed by a very good split here, and then RSS will reduce with a large amount. So smaller trees, it will result in smaller trees, but it is too short-sighted. All right. So using this RSS method, yeah, it might work, but then it's too short-sighted, like RSS at each point, because it does not know that that's where RSS is going to drop by a very large amount, and then we immediately reach our threshold. It doesn't know that it's going to split by RSS that is relevant at each node. So it's short-sighted. So yeah, it will result in smaller trees, but it is too short-sighted. A better approach is to grow a very large tree. We grow a very large tree that is large, with just going, and we call that the T node, or the initial tree, the father tree, the mother of all trees that we have grown, and then we prune it. We use a process called pruning, and then we prune the tree in order to then create a subtree. and then we create a subtree from that father or whatever, the father of all trees, and then we prune it here, and you say, yeah, we're cutting it off here, and then we have a subtree. That's what we can do. At least there we have seen all RSSs. We have seen all RSSs, and this tree is not short-sighted. It is not short-sighted, right? So the goal is to get a subtree that leads to the lowest test error rate, right? We've grown this tree. So given, and then we create a subtree. So given this subtree, test error can be estimated using cross-validation, right? Cross-validation can be estimated using cross-validation. So what we're going to do is cross-validation. The naive way would be to say, okay, we've grown this tree for as much as we can. We have created the father of all trees, the T naught, right? And then let's start creating subtrees. We create this subtree here, create a subtree there, create a subtree here, create a subtree there, create a subtree there. And then for each of those subtrees, we can calculate the test error rate using cross-validation. That's what we can do. That's the naive approach, right? Test error rate can be estimated using the cross-validation. And then we say, for this subtree, the test error rate was this one. For this subtree, the test error rate was so much. For this one, it was so much. For this one. And then we compare the one that we compare the test error rates for each subtree, and then we choose the one with the lowest test error rate. That's what we can do using cross-validation. But that is the naive approach, right? And it's going to be extremely difficult and cumbersome for us to create all subtrees and compare all their test errors. It's going to be difficult. It's going to be difficult, right? We can use something called cost complexity pruning. Cost complexity pruning, right? Cost complexity pruning, or in some books they call it the weakest link pruning. So rather than looking at every possible subtree, we consider a sequence of trees indexed by a non-negative training parameter alpha. So here we're going to have a non-negative. We're going to index the subtrees by a non-negative tuning parameter alpha. So this part is a bit technical, but I hope you understand. We're not going to get into the mathematics. We're just going to discuss the high levels of how this works. So this cost complexity pruning, the process goes like this. So this is the process. We grow a large tree. We grow a large tree T naught using recursive binary splitting like we have been doing on the training data set, stopping only when each terminal node is fewer than a minimum number of observations. We can say stop when each one has 5 observations. The terminal node has 5 observations. Then we stop. So we grow that large tree, and then we are going to apply cost complexity pruning. Complexity pruning to the large tree, to T naught, to the large tree, in order to obtain a sequence of best subtrees as a function of alpha. So we're going to create best subtrees as a function of alpha, right? And after we have created the best subtrees, we are going to use k-fold. We are going to use k-fold of those best, k-fold CV. Apply as a function of alpha. Here we have created only the best subtrees. We are not looking at every, we're just looking at the best according to cost complexity pruning. It selects the best ones, and then we are going to use k-fold CV to choose the best alpha, right? So to choose the best alpha, what we're going to do is we're going to just divide our training observations into k-folds. That's the normal CV, and then for each one of the k-folds, we evaluate the MSE or the error. We evaluate the MSE for each one of the subtrees, evaluate the MSE, and then we will average the results. We average the results. It's like normal k-fold. Average the results for each value of alpha to minimize. So yeah, we're just getting the average error. So what we're basically saying is we have our best subtrees, right? Best subtrees. We have a best subtree that is a function. They are functions of alpha, right? They are indexed by alpha. So we have a subtree alpha 1. Let's just say alpha 1, subtree alpha number 2, base subtree alpha number 3, and so on. So for each one of these we do k-fold. K-fold is basically, we are going to say for each fold we are going to calculate the MSE, and then we average them out. We'll be like, okay, so the average error for alpha number 1 is this, for subtree number 2 is this, for alpha number 3. This is simple k-fold. I think we discussed k-fold in like previous videos, right? And then we have our average errors for each one of them, and then we are going to return to step 2 and choose the subtree that is indexed by alpha, best alpha. And best alpha would have chosen it using this CV. We'll be like, oh yeah, so the best alpha is alpha 4, and then we come to step number 4, and then we choose that tree that is alpha number 4. So that's basically the high level of the process that we are going to do here. For each value of alpha though, we are going to say for each value, for each alpha, someone will be like, but what are those subtrees? So for each alpha there is a subtree. There's a subtree so yeah, it's contained in this father of all subtrees, right? Such that there's a subtree such that this, let me write it, the equation here, m equal to 1. Bear with me, I'm just going to write the equation and then I'll explain what it means. Element ym yi minus yrm squared plus alpha t. Cool. It's going to be something like that, right? So here let's explain what this equation. So for each alpha there's a subtree such that this is as small as possible. This is just as small as possible, right? It's as small as possible. Cool. So let's explain what the symbols mean. What this one here, this basically just means the number of terminal nodes. It's the number of terminal nodes. Number of terminal nodes of tree T. Right? And we know that our RM is just going to be the rectangle or the region or subset of predictor space. Corresponding to region number M, corresponding to the mth terminal node or region, because you saw that our terminal nodes, those are our regions, right? So this is the rectangle or subset of predictor space corresponding to the mth terminal node, right? And this is just the mean for all observations in RM, in that rectangle in RM, right? So basically, yeah, these are the number of nodes, number of terminal nodes, right? So for each alpha, there is a subtree such that this one here is going to be small. depending on the number of nodes that we would have put here. Right? So the tuning parameter alpha, this tuning parameter alpha is called the tuning parameter. It's going to be called the tuning parameter. The tuning parameter alpha controls a trade-off between the subset's complexity and its fit to the training data. When alpha is equal to 0, let's explain that part. When alpha is equal to 0, the subtree, we are not pruning the subtree. The subtree now just becomes equal to the T naught. So T is equal to T naught, because this falls away, and then we have this equation here. We just have this equation, which is that equation for the T naught, right? As we increase this alpha, there is a price to pay for having a tree with many terminal nodes, because we want this to be as small as possible. So if alpha now starts increasing, when we increase our alpha, we cannot have many terminal nodes anymore, because otherwise this thing is going to increase. If we had 20, and then if we had 20, let's say our terminal nodes were 20 and our alpha was 5, was 5, right? If we increase our alpha to 15, we cannot maintain our terminal nodes at 20. Otherwise, how is this going to be small? We want this to be small, right? So which means there's now punishment for us having those 20. We might now have terminal nodes 5. We might now have just 5 terminal nodes. As an example, this is just a rough example. So as alpha increases, there's a price to pay for having a tree with many terminal nodes. And so this quantity here, this whole equation will tend to be minimized for a smaller subtree. As we increase our alpha, we are now going to punish our terminal nodes. And then when we punish our terminal nodes, we are saying now you can't now have many terminal nodes at the end there. You are only going to have 5. And this can only happen for us to have 5. It means we have a smaller tree. When we have many terminal nodes, it means we have a large tree. So basically, let me say that statement again. As alpha increases, there is a price to pay for having a tree with many terminal nodes. And so this quantity will tend to be minimized for a smaller subtree. It will be minimized for a smaller subtree. So our alpha will help us do that. It will help us create small subtrees. So that's basically the process. That's basically the high levels of the process itself. The process is index here, grow a large tree, and then you apply the cost pruning. We are going to see, especially when we do the codes themselves, you're going to see this process at work. You're going to see this process at work when you now apply our CV model, when we are coding in R. But that is the high level process. There's some maths involved, and we are not going to get into the mathematics. But just know that this alpha will help us prune the tree in such a way that we end up with a small subtree, but we don't have to look at each and every subtree. We don't have to look at each and every subtree. It helps us just compare the best subtrees. In the next video, we are going to look at something. We're going to look at classification trees. Here we are looking at at regression trees, and we're talking about the mean and stuff like that. But now we're going to look at classifications, the basics of classification trees. So stay tuned for that video.